the average value, okay, the average of the y's in each group, okay, and that's symbolized. Let's say we symbolize that by m1. So for those variables, for those particular measurements that are belonged to the dichotomy that's coded as a 1, we calculate their average. We take away from that m0, in other words, the average of those particular measurements that are falling into the dichotomy that's coded as a 0. Divide that by the standard deviation of the y variable, okay? And then that's multiplied by the square root of p times q, where p represents, let's say, in the first group, in the group that's labeled as a 1, it represents the size, the number of observations in that particular group. In this case, there's 1, 2, 3, divided by n, the total sample size, okay, the total number of paired observations. And similarly, q is equal to the number of observations that are coded as a 0, the size of the dichotomy coded as a 0, divided by the total number of observations. And straightforward to calculate the point-Biserail when we have a dichotomy on an interval. A true dichotomy, males and females versus maybe salary, okay? It just requires us to break it up into the two groups and to calculate the means of each group on the dependent variable or on the y variable, the standard deviation of the y's, and also the proportion of observations that are falling within each of the groups. So that's point-Biserail for a dichotomy versus an interval. The next one is, let's say, is eta. So this time, so we have, let's say, the Eta Correlation Coefficient, and we use eta when we're dealing with a multichotomy, versus an interval scaled variable. Right? Now, this is, if you think about it now, yeah, what we have is, this is like, let's say we go back to, let's say, in an ANOVA, okay, maybe where we have three groups. We have three groups, A, B, and C, all measured on a dependent variable, 4.3, 6.7, 2.5, 1.3, 1.4, who knows yet. We've got all of these measures within the groups. Okay? And what we're actually going to do is the Eta correlation coefficient is defined to be, from an ANOVA perspective, the sum of the squares between the groups divided by the total sum of squares, and it's the square root of that particular value. The total sum of squares, don't forget, is the same as, so this becomes the sum of squares between divided by the sum of squares within plus the sum of squares between, okay, as a square root of that. From an ANOVA perspective, the sum of squares between, let's say, sum of squares between is simply equal to, so let's say x, once again, is our multichotomy, and there's a number of levels on it. Let's say there's k levels. So we have, in this case, 3 groups. Well, maybe we have k groups, okay? And y is going to be the dependent variable. So it's equal to, the sum of squares between is equal to the distance between, each group's mean, okay? So the y value for each group, okay? The distance away from a global mean, which is the pooled mean value for all of the observations. Let's call that y bar, big G, and it's the square of that, scaled by the number of observations in each group, and it's the sum of all of that. The sum of squares within measure, let's say our sum of squares within measure is going to be, it's just the sum of squares for each group. It's the sum of the sum of squares for each group. So for each group, we'll have the observations minus this respective group mean, and we square them. And what we're going to do is we're going to sum that up across all of the groups. I should really have maybe a subscript G here, to say that the summation is done across the k groups that we have. Okay. So the Eta correlation is straightforward to calculate. It's, once again, it brings us back to the ANOVA table, and it's the ratio of the sum of squares between to the sum of squares total associated with the ANOVA. And typically when you do an ANOVA calculation, you can actually get that correlation out. Let's say if you're using the likes of SPSS, and so on. So where are we now? So now what we've covered. So what we've covered now is we've done Pearson, we've done Spearman, we've done Kramers, we've done Phi, we've done the Point-Biserail, and we've also done the Eta Correlation Coefficient. So now what we have left is these four, let's say, as Weary said, the four missing correlations. So let's try to present a formula for them. Now this is where things get a little bit tricky. And I'm just going to give the formulas. I'll send you back to that particular video if you really want to be able to maybe I'm actually going to do videos on the calculations themselves. So what about when we have a rank variable versus an interval variable? In other words, an ordinal versus an interval variable. Okay? The correlation is going to be or I to represent the ranking variable ordinal along with an interval. And what we're going to do here is that this is if you think about our variables now, so we have, once again, we have this time excuse me, we have our ordinal variable, our ranking variable, and we have our our interval variable, and we have measures, paired measures across these. So, or in this case, represents our ranking. So what we're going to do is it's going to be the product. It's going to be the sum of the cross products, of the ranks with the variable. So it's the RY divided by the total number of observations minus the total number of observations plus 1 divided by 2 times the mean of the Y variable, okay, divided by, see, this formula is really, really vicious looking, okay, divided by n squared minus 1 all over 12 times the standard deviation of the Y, and it's the square root of that. Look, I really probably need to do a video on how to do